So let's finish up 3.4. So we got our 3.4b. And we're going to look at logarithmic equations. And I'm just going to go with that. In 3.4a, we sat there and looked at those exponential equations. So everything was written exponentially, and then we went through and we solved them. So today, it's almost like just the opposite, right? We're going to actually look at those logarithmic equations and then kind of go through and solve them. So I think I got like 4 examples for us to go through, kind of like what we did yesterday, right? So let's just jump right into it today, right? So let's say we have log base 4 of x plus 3 equals 2. So we don't want to sit on our calculator and keep putting in values for x until we can come up with a solution, right? We want to be able to look at this and see if we can actually solve it for x, kind of using some algebra type skills, right? So for us, when it comes to our logarithms, it's kind of hard to, well, there is a way, but we have a base 4 system, not a base 10 system, which we're used to. So with that base 4 system, it's kind of hard to figure out what number goes in there. So when it comes to our logarithms, we can always take a logarithm and we can actually write it as an exponential, right? If we go back to the beginning of the chapter, that was one of the whole sections, right? We switched from logarithms to exponentials and exponentials to logarithms. So when it comes to us having that word log in there, it's kind of, they used to have these big old sheets of paper with all of the different log values, right? Granted, now we have some calculators that can help, but we don't have a calculator that's going to solve this for x. So we're going to take our logarithm, and guess what we're going to turn it into? Starts with an E. Yeah, an exponential function, right? So when we look at our problem, what's our base? 4. Yep. What's our exponent going to be? 2. And that's going to equal our number, x plus 3. So remember when we went back and forth between exponentials and logs? Your number out front is going to be your exponent. Your little guy is always your base. And then that is always the number that we're going to equal, right? So now that I switched it into an exponential function, we can kind of go through the algebra. 4 squared is 16, and that's going to equal x plus 3. Anybody know how to solve it for x? Minus 3 from both sides, right? And what are we going to get? X equals 13. Right? So if they want you to solve a logarithmic equation, the first thing you're always going to do is make it an exponential, right? And then we can kind of work through the algebra. So let's spice it up just a tad, right? And let's say we have 3 times the natural log of 2x equals 12. So because I know I have a logarithmic equation, I know my ultimate goal is to turn it into an exponential and then do some algebra to it. But I want to get it to where my natural log, or my log little piece, natural logs and logs work the same way. I want to try and get it to where I only have that natural log piece or that log piece kind of like all by itself. So I want to get it into the simplest form. So I want to be able to get rid of this 3. So I'm going to divide both sides by 3. And then now I have natural log of 2x equals 4. Everybody good on that step? Right? Now we want to turn it into an exponential. And we all know what natural log stands for. Natural log stands for log base e, right? So now I have log base e of 2x equals 4. And then now I can work on turning it into a nice little exponential. Right? My base is e. Whoops. My base is e. My exponent is 4. And that's going to equal 2x. What am I going to do to get x all by itself? Divide by 2, yep. So we have e to the 4th divided by 2. Find our trusty handy dandy calculator. All right. Put e to the 4th divided by 2 in there. And I'm going to go with, we get an approximation, right, of, I'm going to go with 27.3. Feeling confident-ish? Maybe? We good so far? Alright. Spice it up a little more. Just throw them all at you. Alright. So let's go really nice and long and nasty. Let's go with log base 2 of x plus log base 2 of x minus 7. And let's say that all equals 3. So now we got to go back to all that knowledge that we get from the beginning of this whole chapter when it comes to our logs. Because remember, we want to simplify that log down as much as possible before we sit there and try and switch it into an exponential. So I know that I can condense this log. Right? When I have 2 logs that are added together, I know that I can rewrite that using multiplication. So this would be the same thing as log base 2. And I'm just going to throw it in brackets just to kind of keep it all together. X times x minus 7. Right? And that equals 3. And granted, we're going to multiply that guy out, but I'm just going to leave it the way it is for a moment. Okay. So now my log is condensed as much as I possibly can condense it. So now I can change it into a exponential, right? What's my base going to be? 2. Right? My exponent is going to be 3, and that's going to equal that x times x minus 7. Okay. Do some lovely algebra. 2 to the 3rd is 8. Then I'm going to go ahead and use my distributive property, and what am I going to get? X squared minus 7x. Oh, it's a quadratic. Do we know how to solve quadratics? Yeah, we know how to solve quadratics, right? Get everything on one side. So 0 equals x squared minus 7x minus 8. All right. And then when it comes to the quadratic, you can solve it whichever method you are comfortable with. You can go straight into figuring out those factors, or some of you guys might like to use the area model, right? What do we got? We got x squared, and we got our negative 8, and we're trying to figure out how to separate that negative 7x into 2 terms, right, to fill in our box. So we know we got to multiply to get a negative 8. So we know one's got to be positive and one's got to be negative. And we know that when we combine those two terms, we have to get a negative 7. So we know we're going to multiply by a negative 8 and a positive 1. Right? Then we're going to pull out those common factors. So on top I'm going to get an x. Over here I'm going to get a positive 1. Then you get an x and a negative 8. Right? So this guy factors into x plus 1, x minus 8. And some of you guys can get to this point without doing that area model, right? And that's great. By all means, if you can do it without doing the area model, do it without the area model, right? So then the zero product property tells us that if we're multiplying things together and they equal 0, one or the other has to equal 0. So either x plus 1 has to equal 0 or x minus 8 has to equal 0. So now we're going to get an x equals negative 1 and an x equals an 8. Right? So a little tidbit of information when it comes to logarithms. If we were to plug this into our equation and we plug in that negative 1, it's not going to work. So when it comes to logarithms, we can only look at our positive values, and our negative values don't work. You can't take a log of a negative number. So sound like a plan. Yep. And you can always check those numbers by plugging them in to see what comes up of it. Like if I were to test that 8 into that original, I would have log base 2 of 8 plus log base 2 of 8 minus 7, and I want to know if that equals 3. So this guy, right? You're looking for 2 to what? Right? 2 to what exponent is going to give you 8? That's going to be 3, right? 2 to the third is 8. Plus, on this one, 8 minus 7. That's the same thing as putting a 1 there, right? So 2, your base is 2. So 2 to what exponent is going to equal 1? 0, right? Anything raised to the 0 exponent is 1. Equals 3. So 3 equals 3. If I try to do that with the negative 1, I would have log base 2 of negative 1 plus log base 2 of, what would it be, negative 1 minus, negative 1 minus 7. So just looking at this part, I'm saying, so my base is 2 to what exponent is going to equal negative 1? It's not going to happen, right? So that's why we can't use those negative numbers. We can't have negative logs. So we're just going to have x equals 8. Not bad? You guys thought you guys were done with quadratics, didn't you? They just keep coming back to haunt you. Alright, one last one. Throw some words in there for you guys. You guys like words, right? You guys like to talk. Alright, so our fourth example. So I'm going to give you guys an equation. We're going to say like A equals 3.6 or 36.1 e to the 0.012 with a t up there. And this equation is going to model the population of California. Or if you want to change the state name, you can definitely change the state name. Right? I was just thinking of someplace nice and warm. And this is being represented in millions. And t is going to be our time, right? So this is t years after the year 2005. So they came up with this equation 15, well now pushing 16 years ago, right? So we can ask you guys some questions when it comes to this little model. So what's the population in 2005? So can I just write population in 2005? So they like to give you problems like this to see if you guys are paying attention kind of almost to some key words in there, right? So in the directions or in the explanation, that equation for that population, what does T represent? The years, there's a key word, after 2005, right? So if I want to figure out the population in 2005, okay, so A is my population, 36.1 times e to the 0.012. What am I going to put in for T? Anybody want to guess? 0. Yep, absolutely, right? Because 2005 is 0 years after 2005, right? So we just got to be careful not to put some people want to put a 1 in there, right? Because that's where we're starting. So we're going to put a 0 in there. So we're going to get 36.1 million, right? Now, if you wanted to figure out that population in 2006, right, A is going to equal 36.1 e to the 0.012. What are we going to put in for T now? We're going to put in a 1, right? Because 2006 is 1 year after, right? So make sure we're looking for those key words, and especially if they put in there like an after or a before. Okay. So now let's try spicy. Let's go with, when will the population reach 40 million? When will the population reach 40 million? So now when we look at our nice little model, we got to put that 40 in for A, because right, A is our population. So we want to know when we're going to get a population of 40. So equals 36.1 e to the 0.012 t. So now we're looking at problems that we were just working on a few minutes ago, right? We want to get our e all by itself. So we're going to divide by that 36.1. So we get 40 over 36.1 equals e to the 0.012 t. I'm going to run out of room. You think you can get your bases to be exactly the same? No. So we're going to take the natural log of both sides. Woo. Sorry. There you go. Right. So on the left, we're still going to have that natural log of 40 over 36.1. What happens when we take the natural log of e? We get whatever's in our exponent. So that's going to equal 0.012 t. Get t all by itself, you're going to divide. So we got the natural log of 40 over 36.1, all divided by 0.012, and that's going to equal our t. We're going to put that into our fancy dancy handy dandy little calculator. So the natural log of 40 divided by 36.1 divided by 0.012 is going to give us 8.55. Right? So t is our time after 2005, right? So we need to figure out what year this is going to be. So it's going to happen in the 8th year after 2005, right? So 2005 plus that 8 years, 8.5 years technically, but 8 years is good enough. And that's going to give us what? 2013? Right. So the population in California would have reached 40 million 8.5 years after 2005, so in 2013. My word of advice is when it comes to working on these problems, like we waited until the very end before we did any of those computations on those numbers, because every time you go to put it into your calculator and you start rounding those percentage or those decimals, you get farther and farther away from the actual value, right? Because you keep rounding, you're rounding, you're rounding, and you're rounding. So you're going to end up, because these little minute changes is going to make big changes when it comes to logarithms. So I always wait, just do the algebra, do all of the, moving the things around until you get down to where you can't simplify it any farther. I have it solved for t, then plug all of this into the calculator.